So in previous videos, we worked out an expression for the current I in an LC circuit like this. And what we found was that I is square root of capacitance over inductance times the starting voltage, V naught, times sine omega naught t. And omega naught is the natural frequency, and we said that omega naught was equal to square root of 1 over L times C. And V naught is the starting voltage on the capacitor. And our original assumption was that I was 0 to begin with. And that's the expression for the current. So what I want to do now is a specific example, and we'll do that down here. First, I'm going to install a switch into our circuit so that we can add some energy and it won't go anywhere. Then for C is going to be equal to 1/4 of a farad, and L is going to be equal to 1 Henry. All right? And on the capacitor, I'm going to put enough charge to bring this up to 10 volts before we close the switch. And then at time equals 0, we'll close the switch. And what we want to find is, what is I of t? We have L, we have C, we have a starting voltage, and so now we have everything we need to work out the current. Let's do that, okay? So first off, we'll do omega naught. Omega naught equals 1 over the square root of LC. So that equals square root of 1 over 1 Henry times 1/4 farad, which equals square root of 4, or equals 2. And that's in units of radians per second. That's the natural frequency. We know the natural frequency right here, and now we can work out the rest of it. So we can just fill in I equals square root of C, which is 1/4 farad, divided by 1 Henry, times V naught. V naught was 10 volts, times sine omega naught t. Sine omega naught is 2t. And finally, I equals, this is the square root of 1/4 or 1/2. So that's 1/2 times 10 is 5. I equals 5 sine 2t. So for this specific circuit, that's the answer for this current here. Now I want to show you what that actually looks like. So this is a plot of I of t equals 5 sine 2t. And this is what a sine wave looks like with time. So the axes are time in seconds, and this axis goes up to 5 amperes and then down to minus 5 amperes and continues on that way, and it basically goes on forever. And what I want to do next is work out the voltage in the circuit. We didn't talk about the voltage yet. So I'll sketch the circuit again here. Here's L and C, and this is the voltage right here, voltage across both guys. We've already worked out I. And now we want to find V. What's V? That's what we're looking for. So we know that I equals 5 sine 2t. And to find V, one of the easy ways to find V is to use the inductor equation. And we know that V equals L di dt. That's just the basic inductor IV equation, right? And let's see what happens here. V equals L is 1 times di dt. So that's d dt of 5 sine 2t. Now let's take that derivative. Okay, I'll go up here. V equals 5 comes out of the derivative. Sine 2t. The derivative of sine of 2t is 2 times cosine of 2t. All right, so our voltage solution is 10 times cosine 2t. So something interesting just happened here. Let me show you. We started with the current being a sine function, and we eventually took the derivative of that sine function, and now we have a cosine function. So we went from sine to cosine for voltage. That means the voltage doesn't look quite exactly like the current. Okay, let me show you a plot of the voltage. Here's the voltage here. This is V of t. And that we decided was equal to 10 cosine 2t. It starts at a value of 10 at time equals 0, and then forms a cosine wave that goes up and down between plus and minus 10 volts. Now let me show you what it looks like when we plot both I and V on the same graph, and we can see the timing relationship between them. So this is a plot of I of t in blue and V of t in orange. One of them is a sine wave, the current is a sine wave, and the voltage is a cosine wave. So this is what we were going for. This is the natural response of an LC circuit, and we had two specific component values in it. We saw that we came out with both current and voltage looking like sinusoidal waves. This LC circuit, this is where sine waves come from in electronics. It's pretty cool.